Hi, I got this little voltage regulator block designed for use in model airplanes. Got it in a previous mailbag segment, took a quick look at it, and I goofed that up at the time, so I thought I'd have a more detailed look at it. Keith sent this in, and him and his model airplane buddies wanted to know if this thing was any good. It's from a company called Castle Creations, and it's the BEC Pro. BEC is a battery eliminator circuit. It's designed to power the solenoids and the receivers and other things in a model airplane from the high voltage model airplane battery itself, so you don't need a secondary battery and things like that. So you wanted to know, this thing's cheap, it's like $38 or something, which is apparently cheap for one of these things, and he wanted to know if it was any good or not. We took a quick look at it in a previous mailbag, but I thought we'd actually check the output power, actually power the thing up and see if it's any good, because it's supposed to have a maximum continuous output current anywhere from 8 amps up to 15 amps here, depending on the input voltage, and it has an adjustable output voltage as well, anywhere from 4.8 volts to 12.5 volts. And if you take a look at the figures here that this thing claims, the input voltage for specified anywhere from 16 to 48 volts, depending on what type of battery you've got. In this case, it tells you like an 8-cell battery, 10-cell, and a 12-cell. That's what the S4 12-inch series stands for, and so it can go anywhere up to 50 volts. And of course, it's going to have a varying output power capability. So here is the output current, and Keith said that he's set this one to 6.5 volts, so I don't know how to adjust it. We'll just keep it set to 6.5 volts for the purposes of today's experiment, and these are the maximum continuous output powers, just multiplied at 6.5 volts times the output current here at different input voltages, and it can be anywhere from 52 watts up to 97.5 watts in this tiny little heatsink here. And as I mentioned in the previous mailbag, that sounds a bit sus, because a heatsink like this is only going to have a certain amount of power dissipation capability, roughly, I believe, about, for this type and size one, about 6 degrees C per watt. So for each watt dissipated, it's going to increase by 6 degrees. We'll go into details in a minute on that. And this is a DC to DC converter, of course, and it's going to have an efficiency of at best 90% at one of these particular things. They would have designed it at for one particular output current, because you can design DC to DC converters with 90% plus efficiency if you choose the correct type of magnetics, i.e. the inductor here. That's what this big device is, the MOSFET, the output capacitance, and the switch-in frequency, and you can actually design it for quite reasonable efficiency. So let's say it's 90%. If you're getting near 100 watts here, let's just say it's 100 watts, at 90% efficiency, this thing has to dissipate 10 watts. So that's going to cause a temperature increase in our active semiconductors that are dissipating the power here. Namely, we've got our two MOSFETs here. These are D409s. You might think this is the MOSFET, but it's not. Dead giveaway here is not connected. An A for anode, and the other one would be the cathode here. That's the diode. And of course, the inductor here will be dissipating power as well, but because that's not an active semiconductor with a maximum junction temperature where the magic smoke can escape, that one's much more hardy than the other. So we're really concerned about these devices dissipating power, and because the heatsink's on the other side of the board and they've just got vias underneath these going down to the other side, actually transferring the heat from one side to the other, we're going to get losses in there. So you've got your junction to case losses, and then you've got your case to PCB, then you've got your PCB from top side to the bottom side, those losses in the vias, then you've got your contact thermal resistance with the heatsink, and then you've got the thermal resistance of the heatsink as well. And I've done videos on thermal design and things like that, so I'll link those in if you want to check them out. But yeah, we're really concerned about these heating up with such a small heatsink with a large power dissipation like this, 50 to 100 watts. You cannot design it to have 90% efficiency at each of these input voltages. When you design a DC to DC converter like this to operate over a wide voltage range and a wide output power range, Due to various factors in the design, you just cannot get a general purpose wide input voltage and a wide output current range to have a universal high efficiency across all the input voltages and all the output powers. So if we have a look at the datasheet here for the actual device used in this, which is the LTC3824, which is a high voltage step-down controller, goes up to 60 volts. This is exactly what you would use here. It's a pretty decent controller. And take a look at the efficiency and power loss versus load current graph on the right there. You can see that the top one with V in equals 12 volts. Look, it approaches that 90% efficiency that I was talking about there, but at higher input voltages, V in equals 40 volts, it's a different curve entirely. And we're looking at, say, 40 volts, depend like at a couple of amps, for example, but this is based on which particular transistor you pick and inductor and everything else, right? Because this doesn't have the switch-in MOSFET built in. But, you can see it drops down to, it could be well under 80%. 75% efficiency would be fairly typical of something like this at a higher voltage, unless you specifically designed it for high voltage use only at one specific input voltage. And that's a disadvantage of a design like this, is that the efficiency is going to vary quite drastically over that input voltage range and output current range as well. So it's always going to be a compromise, which is why the specs for this thing actually show as the input voltage rises. You saw on the specs on the back of the thing that the maximum power dissipation in it drops. The efficiency of a typical DC to DC converter, and it's going to have something like that. There's going to be a peak voltage and current where it is at its most efficient, but at lower than that, the efficiency is going to drop off. At higher than that, the efficiency is going to drop off. And when the efficiency drops off, you dissipate even more power in your heatsink here, and, well, that ruins your day. So let's see if this thing can meet its claims here of a maximum continuous output current. Let's go. I'll just mention briefly, though, the capacitors, because these will be a big failure point in these things. If these are wet electrolytic capacitors, then they can dry up and, over time. And, of course, the output, the ESR increases and their life expectancy goes down. So, pretty terrible. We've got 105 degrees C rated electro over here. This is on the input. And our two output caps, these actually don't look like wet electrolytic dielectric material. They actually look like a polymer capacitor, or what's called a solid electrolytic capacitor, i.e. there's no liquid inside them, but that doesn't mean they still don't have a maximum lifespan. And I'm not 100% sure that they're solid polymer types, but you would have to look up the specific data sheet. I didn't have any luck with that particular part number or whatever, but it's got no vent on. There's no score marks in the top for venting, and that, if you see those, then that's a dead giveaway that it's a wet electrolytic capacitor, your traditional electrolytic capacitor that's going to have a shorter lifespan at higher temperatures than the solid types. And it's a myth that all of these surface mount types are solid. That is not necessarily the case, and just because it doesn't have a score marker vent in there on the top, then that still doesn't guarantee that it's a solid type. This could still be a wet electrolytic type. Anyway, just thought I'd point out the difference there. Anyway, let's give them the benefit of the doubt. Those are properly spec'd solid capacitors, and by the way, that nice shine on there is a conformal coating, so that's very nice. That's something that's used in like an outdoor RC plane. Anyway, let's hook this puppy up and see if we can measure its performance. And they've basically got the wiring on this a bit back to front. Look at the nice beefy 16 gauge wires they've got on the input here, but the input is going to be lower current than your output. The output thing, as you saw, this thing has a maximum of 15 amps. And then you got, we've got two wires in parallel here. Okay, so it may do the business, but, we've got these tiny little piddly connectors which aren't going to do the current. You can, of course, put them in parallel like that, but, 15 amps, these are going to get maybe 5 amps each, so, like tops. So, really, you can't do the maximum 15 amps with just these two. Anyway, let's cut these off and have a look at the wiring inside here to see if it's adequate. Oh yeah, that's pretty decent. That's pretty decent. There you go. No worries. You put two of those in parallel, we'll be hunky-dory. So to test a regulator like this, we need a power supply. Of course, I'm using my Rigol DP832. Now, this is only maximum capable of 30 volts, 3 amps per channel, but because it's got 2 channels, or actually 3 here, we can put them in series. So that's why I've got this wire here just looping the positive and negative like that, and then we can get a maximum of up to 60 volts. So we can go right up to that 48 volt input capability easily with this. And the good thing about this is that it has power output as well, but of course any decent power supply is at least going to display voltage and output current, but this will display our power as well. So we know our power input to the module itself, and we know the power output. And the other bit of gear we need is an electronic load. You can actually use a resistive load if you've got those. You can cobble them together, but a nice precision electronic load like this BK Precision 8601 can't beat it. And we can set the output current. So what I'm going to do is actually set the output, the constant output current to, in this case, 8 amps, and it'll tell us the output power, and in this case it is actually telling us the output voltage. But we need to do one more thing with this setup, because these output leads are really actually quite wimpy. There's at like high currents, like we're talking 8 to 15 amps here, we're going to get serious voltage drop across these leads. So we're actually going to get power dissipated into that, and our figure on here will not be accurate for our output power. So conveniently, we've got the second one here, and we're going to actually wire it into the back of this BK Precision unit for the remote voltage sense terminal. So it's going to sense the voltage directly on the output here. So at the moment, because there's no load, the output voltage at the terminals here is going to be exactly what the output voltage here. So there's no current flowing at the moment through these cables, so there's going to be no voltage drop, but at 8 amps, it's going to be very significant. All right, let's test it. I've set both channels here to 24 volts, so that's going to give us a 48 volt output, and if we have a look at the data we had before, 48 volts, its maximum rating is 8 amps continuous, so I've set the 8 amp up here on the electronic load up here. We'll switch it on in a second. And it should, well, it claims to have a maximum power dissipation capability based on the output current here of around about 52 watts. Let's just call it 50 watts or thereabouts. So at 48 volts input, at 100% efficiency, and with 50 watts output, we need to supply, this power supply needs to be capable of supplying 48 volts at 1 amp to give that 50 watts. It's easily going to do that. It's got 3 amp output capability. So I'll set the maximum output current here to 3 amps because, look, we don't need to protect this thing. I don't care, it's not the design phase. This is supposed to be a finished product. It's supposed to work. So I could set the limit, if you were testing a design, your own DC to DC converter, just to be safe, you would set the output current to 1.1 amps per channel or something like that. But you do have to be careful setting a low safe, in quote marks, current output limit, because you can get certain like power on surge currents, and that may up, and then the power supply that you're powering your converter with may go into current limiting mode. It drops the voltage, and then that causes a problem with your converter, and well, that can ruin your day. So anyway, I just got to set to 3 amps. Let's go. So what I'm just going to show you now is if I don't hook the voltage sense lead up to the rear voltage sense terminal of this, you'll see how much voltage drop we get across these cables at this 8 amps continuous current. So let's turn our load on. We've got, everything's right. Let's switch it on, and we're getting 6.6 volts at the moment. So let's switch it on. Bingo, it's dropped down to 6.18 volts. So it's reading 6.18 volts directly on these terminals here. And so there's going to be some loss in these leads. I can actually measure the other 2 wires hooked onto here and see what we get. And you can see that if I use my meter here to actually probe directly onto the output of the brick here, so I'm measuring just directly on the output terminals, you'll see it is still holding at 6.55 volts. So it seems to be handling that 52 watts just fine and still giving our set output voltage, but you'll notice that it's only reading 6.1 up here. That's because of the loss in the wires. So if we take these two wires and don't short them out, if we take these and plug them into the rear sense terminals and switch the voltage sense from the front terminals to the rear, we'll be able to get a more accurate reading. And this is actually important because you'll notice that our BK precision load up here is calculating an output power of 48.93 watts. And that is a very significant error because our meter here is showing that it's 6.56 volts here. So if you go 6.56 volts times the 8 amps, which this is actually measuring, okay, then that's going to give us a value of 52.48 watts. That's the true 52.5 watts is the true output power being delivered from this module. But we've got that error, very significant error, up there on the BK Precision. So that's a trap for young players. Make sure you use the external reference input. I'll show you how it works. And here's the sense terminal on the back. You can actually see positive and negative sense terminals. So just hook these wires directly to the output terminals of the power supply module that you're testing. So we'll turn our remote sense terminal on. Bingo. So let's try that again, shall we? 8 amps constant current load on this thing, 6.59 volts with no load. Turn it on. Bingo, it drops down to 6.58, exactly 55, exactly what we saw on the multimeter before. So that's a big trap for young players, and bingo, it's showing the 52.46 watts. So now we're getting an accurate measurement. Trap for young players, voltage drop on the output leads. Now, just because this thing works doesn't mean that it's any good. Okay, it's outputting the set 6.55 volts, no problems, at the rated 8 amps continuous output for a 48 volts input. No worries, but what's the efficiency of it? How hot does it get? Is it going to last 5 minutes? Is it going to last 5 hours? Or is it going to last 5,000 hours? Because it may shut down any second because of thermal overload. We don't know. So if we have a look at the input powers here, look, 35.25 watts, 35.25 watts. Okay, so we add those together because we've got series. Well, hang on, folks. You'll see something starting to happen. The voltage is going up. The input powers, I think, and hang on. Yeah, that's starting to smell pretty toasty. I think we've got a problem. Anyway, we add up these two powers here. That's our input power. Oh, bingo. Well, it just died. I think, yep, it's cutting out. It's cutting out. This thing cannot handle that with a free air heatsink. And that's what I was about to get to. What we need to do now is measure the heatsink temperature here and see what we're doing. We can use a direct thermocouple probe, but hey, I've got a FLIR E8 here, so we'll give that a whirl, and as soon as it's powered up, here it goes. Hunky dory. Let's measure the center here. Hopefully you can see that. 160 degrees. Yep, it's way too hot. I'm switching that off now. So that is ridiculous, folks. 160 odd something degrees here. Hopefully you saw the temperature up here. 161 degrees with free air, but that's what I would have expected with such a tiny heatsink. It's not going to work in free air like this. But hey, if you have a look at the data sheet for this thing, it actually tells you that it's rated for a certain particular airflow over the heatsink. And of course, the thing is, if that heatsink is getting to 160 degrees, then imagine what the junction temperature in the poor little MOSFETs in there are getting to. It's like these things will shut down, burn up, the magic smoke will escape. So it obviously cannot do its rated current with no airflow. But that doesn't surprise me at all. And we are actually measuring this out of its spec. We need an airflow over it. Anyway, let's take a snapshot here. Let's go 34.8 watts, double that, and then we can calculate our efficiency. So what we've got here is 69.7 watts input power, 52.4 watts output power, which you saw here like this. So that gives us, just divide 52.4 by 69.7, output power over input power, and we can get our efficiency here. So, you know, around about, let's call it 75%. efficiency. So, you know, that's fairly typical of what you'd expect of a DC to DC, wide range DC to DC converter like this. But that means that heatsink, that poor pissant little heatsink there, has to dissipate a lot of power. How much power does it have to dissipate? Well, you subtract 52.4 watts from 69.7 watts, and that leaves you with 17.3 watts it's got to dissipate in that tiny little heatsink. We can have a look at the data sheet for the, well, not this exact heatsink because I don't know the exact heatsink, but I got one. The nearest I could find was this one. It's basically the third one down there on the list, the 625-45. And you can see the thermal performance graph here for the heatsink to ambient thermal resistance in degrees C per watt on the vertical axis there versus airflow on the horizontal axis there. And we're looking at around about 440 LFM here for the starter sheet spec of 5 miles per hour airflow. So if we actually look at the graph here, it's the third one down, and then we take 440 LFM and we then extrapolate that back across, we get a thermal resistance of the heatsink of about 8 degrees C per watt. 8 degrees C per watt is quite large, and we said before that we had about 17.3 watts dissipation in this thing due to the 75% efficiency at this particular input voltage. That equals, multiply those, that equals 138 degrees C temperature rise above ambient. If ambient's like 20 degrees, we're looking at 150. More than 158, so pretty close to what we got there, even with the airflow over this thing, the nominal rated airflow. Notice we measured 161 degrees C, so maybe the heatsink we got slightly better than that because we were getting no airflow, but still, this is way above the maximum junction temperature of the semiconductors. And if we actually have a look at the MOSFET used here, the AD409, then we can see that the maximum junction temperature, absolute maximum junction and storage temperature, 175 degrees C. Of course, we are going to, you might say, well, it's under that. Well, no, it's not, because you have to look below that at the junction to ambient junction to case, and then you've got a couple of degrees C per watt there. You've got to add it on. Then I said you've got the vias, and check out my other video, which I've linked in, where I go through the detailed calculations and show you how to do that. So it's certainly going to add up that this thing, there's no margin in this at all. If it does work, it's going to be extremely borderline for this particular performance. And you can look at the actual diode used here as well and look at its maximum junction temperature right down the bottom there, plus 150 degrees C. So once again, it's actually going to be higher than this. If our heatsink's already at, well, 161 and not with any airflow over it, but you've got all these junction to case, and then the vias going through, and then the thermal resistance of the insulating conductive pad in there, the thermal pad, and everything else. It's just, no, it's really borderline. And because everyone's going to want me to do it, what happens when I blow some air over this thing? Well, let's find out. I've got this little Sunon fan here, and the 5 miles per hour is 2.2 or thereabouts meters per second. So I'm going to get my anemometer here, and I've set it. So it's around about, near enough to that. So now we can blow our rated, reasonably close to it, our rated 5 miles per hour airflow over this thing. So we can repower it up and measure it again. And check it out, this thing's actually doing amazingly well now. It's always amazing what airflow can do. We're looking at, 70, 72, something like that. Over 70 degrees. That's certainly within a decent ballpark. So yeah, I'm pretty darn happy with that. Look, the board's on an angle there, so I'm probably blowing across the parts as well. So that's probably not the best. So what I'm going to do is, because the whole idea was just to do the heatsink. So I'll flip it on that side where the board is down and see if it increases. I probably would expect it to increase a little bit like that when there's now no airflow on the bottom. It's only over the parts, which is certainly going to help, but just over the heatsink. So let's have a look at that now. I've had it going there for a while, and that's actually rather surprising. I'm getting under 70 Now, I would have expected that to increase, but I guess more airflow, yeah, it's angled differently now over the fins, so I guess it's more efficient. And if we try and have a sneaky peek under like that, yeah, we've got the board on a bigger angle now, but yeah, we can, like the case of the MOSFETs, for example, you get in there where, let's call it 100 degrees C, but that's probably still okay. Yeah, I don't mind that at all, especially for the amount of power that we're delivering and that we're dropping. That's, yeah, it's going to do the business. So at 48 volts, we're cooking with gas, but does it work down at 16 volts input for a continuous output current of 15 amps? Well, I've changed to my PowerTech MP 3090 switch mode supply here. It can only go up to 15.3 volts, but I'm going to, you know, say that's got to be near enough. Anyway, I've got the constant current output set to 15 amps. We've got our 6.57 volts, exactly the same as before. Let's see what it does. Wah, 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 wah. It's dropped down to 1 volt. It's dead. So let's say go to 12 amps here and see what it does for 12 amps. Oh, there we go. And yep, she's working at 12 amps. We're getting the output power 78.5 watts there. So yeah, I'll leave that for a while and get some temperature. No, hang on, it's starting to drop. It's starting to plummet. No, doesn't like that. Doesn't like that at all. Nope, it's dropped out of regulation. Wham, Gonski. Anyway, as expected, it's much more efficient down at this 15.2 volts, 5 amps, looking at 76 watts input power, 65.5 watts output power, about 86% efficiency there at the lower input voltage. And because of that increased efficiency, it's running at a much cooler 56 degrees on the heatsink there. Once again though, in free air, nope, you really want the 122. Nope. You really want the airflow. So if you're using this thing for its intended purpose for a model aircraft, you want some sort of, you know, like the heatsink, I don't know, poking out the bottom. I don't know where this would be mounted on a typical aircraft. You don't actually want it like inside the fuselage with no airflow and just like trapped like that, because it's not going to do the job. You really need the airflow over it. It makes a hell of a difference. Anyway, the reason that we're seeing the discrepancy versus the data sheet, like the cool temperature we got on this operating versus the data sheet that I pulled out, this looks like it's about 4 degrees C per watt, whereas our data sheet said about 15 degrees C per watt. Obviously, you know, there's like just the design of the heatsink, it's a similar dimension, everything else, but I think the fins are actually larger on this one, so larger surface area. I think the data sheet one had smaller surface area fins on it, so yeah, that could probably double your thermal resistance of it, and then that makes a huge difference. If you just looked at the datasheet value, then you would think, no, this design is not viable. They haven't left adequate margin. But when you actually, do some tests on this, granted they're not massively controlled tests, but they're, going to give you a decent back of the envelope performance figures, then, this thing is actually a pretty reasonable design at the higher input voltages. But as you've seen here, I've been operating now 10 amps output current, by the way, so 65 watts output power. But no, it basically, from what I see, further testing required, of course, but it basically does not meet that 15 amps at output, continuous output current at 16 volts. It can't even do it momentarily by the looks of it. So yeah, I don't know what's going on there. Further testing required, but at the higher input voltages, certainly it worked just fine, and there's reasonable margin on the design, as long as you got the airflow. So there you go. I hope that's actually finally answered Keith's question. This video was longer than what I thought it would. It's gone for about half an hour or so. But hopefully this is like a tutorial on sort of how to rough and ready tutorial, how to characterize a DC to DC converter. But like there's a ton more stuff we can do with this. We haven't measured it over the full envelope range, and we haven't even checked the output ripple, and like tons of stuff. We could go recharacterize this at every input voltage over every output current, get characteristic curves for the thing, and you can spend days and days or weeks and weeks actually characterizing just a one regulator brick like this if you want to do it properly. So we've just done, a couple of simple spot checks today. Higher input voltages seems to work just fine given sufficient airflow. So anyway, I hope you found this useful, and I will link in at the end of this video the extensive design tutorial. It runs for about 22 minutes. It's well worth watching on SMD thermal design, how to actually dissipate power in SMD packages like is used on this one, and it takes into account the via thermal resistance and goes through all the calculations and graphs and everything else. So well worth watching. Anyway, if you enjoyed it, please give it a big thumbs up. As always, links down below to, or the forum, all that sort of jazz. And don't forget, if you want to support me, there's a Patreon link somewhere down in the bottom corner, right at the end of this video. Thanks for everyone who supports me on Patreon. Awesome. Catch you next time. The copper will have a thermal resistance too, but it can get quite complicated. So I'm just assuming there's no loss in that copper itself. The next one is the via. The heat actually has to, you remember that 10 watts of heat or whatever it is has to transfer through the via. It's going to have a specific thermal resistance, and then it's got to get through that sill pad that we put in there. That sill pad will have a thermal resistance. Look up the data sheet for it. It'll tell you what it is typically. And then we're going to have the thermal resistance of the bar here.